Let's talk about work. In physics and engineering, it's helpful to analyze the amount of work that's being done in a given situation sometimes. Before we talk about how to calculate work, I want to introduce a mathematical topic, a mathematical tool that's called the dot product. The way the dot product works is you take two vectors and you multiply them together in this special way. The way that you do that, I'm going to show you first with an example. So let's say our first vector is the vector 1, 2, and then let's say our second vector is 3, 4. Then the way this works is you just multiply the two x components together. So in this case, 1 times 3 is 3. And then you multiply the two y components together. So 2 times 4 is 8. And then you add those two numbers together. 3 plus 8 is 11. So the dot product of these two vectors is 11. What does that have to do with work? It is definitely not obvious yet, but it does have something to do with work. Let me give you the general definition of the dot product. So if you got two vectors, let's call them v1, v2, and w1, w2. Then to take the dot product of those two vectors, you multiply v1 times v2, and then you add w1 times w2. All right, you can do this for any number of dimensions as well. So 3-dimensional vectors, you can definitely take the dot product. 10-dimensional vectors, you can do the same thing. Probably for most of the audience, the way that you've calculated work or seen it is when you've got an object with a constant force applied to it, and that object moves through a certain displacement. In that case, the work is just force times distance. So that may be a formula that you've heard of. Work equals force times distance. But what if you have your object and the constant force that you apply to it is not in the same direction as the object moves? For example, if you've got a wagon or a suitcase and you pull on the handle, you're applying a force at an angle. So if you take a force that's applied at an angle to an object and then the object moves through a certain displacement, since I want to talk about this in the context of math, let's say the movement is going in the positive x direction, then you can figure out how much of that force is going in the horizontal x direction, and however much is going in that direction, so the x component of the force, you multiply that times the distance, and that will give you the work. So let's say the angle between the force and the horizontal, which is the displacement direction, let's say that angle is theta, then the vector f is the x component of that, we know from trig, is just the length of f times cosine theta, and then the y component is the length of f times sine theta. So if I want the amount that's going in the x direction, that's just f times cosine theta. Then the work is just going to be f times cosine theta times the displacement. Let's call it d. Notice that if we take the dot product of these two vectors, if we take the force to be a vector and the displacement to be a vector, the displacement is all going in the x direction. So the x component of that vector is d, the length, and then there's no y component, it's 0. So if you take the dot product of those two vectors, you get f cosine theta times d plus 0. So the dot product does give you the work in that case. But this seems like a pretty simple situation where you've got the displacement going in the x direction. So what if we take that same type of situation and we rotate it? Let's say we rotate it through an angle of alpha from the positive x direction. Our new force vector, if you take the full angle from the positive x-axis to the force vector, it's alpha plus theta. So the x component is f times cosine of theta plus alpha. The y component is f times sine of theta plus alpha. And the displacement vector now is, it's been rotated also, so its x component is d times cosine alpha, and then y is d times sine alpha. What's the amount of work that's done in the situation if we've just rotated it? When I say we're rotating it, I'm not even saying that we're changing the gravitational force by rotating it. I'm just saying we're basically changing our perspective. We're just like rotating the axes so that it's not lined up perfectly for us. What happens in that case with the work is still the same. You still got the same physical situation, the same amount of force being applied, same displacement. So the work should still be the same, but the vectors are different. So what happens if we take the dot product of the two vectors now? If we take the dot product of these two vectors, then we get F times cosine of theta plus alpha times D cosine alpha plus F sine of theta plus alpha times D sine alpha. So is that correct? Does that give us the work? I can't tell yet, but we can simplify the cosines and the sines. Let's go back to trig, to our angle sum formulas. Remember, cosine of theta plus alpha is going to give you cosine theta cosine alpha minus sine theta sine alpha. And then sine of theta plus alpha is going to be sine theta cosine alpha plus sine alpha cosine theta. So when we multiply it out, you can see that two terms will cancel out. And then we can factor out a cosine theta. And so all that's left is a cosine squared alpha plus sine squared alpha. And if you got cosine squared plus sine squared of the same angle, we know that's 1. So what we have left is F times D times cosine theta. It did give us the work. This is an extremely useful tool for some very complex applications. I'm going to touch on that a little bit in my next video on vector projections.